Good morning to one and all. I am Mark Srinivasachari from ECA section. Today my topic is about the vector signal analogy, a gateway to signal processing. And what is an analogy? An analogy is a cognitive process of transferring information from a particular subject to another subject, and it helps us to understand complex abstract concepts by relating them to familiar ones. And the big idea is we will use our understanding of vectors to comprehend the world of signals. Next one, what is a vector? A vector is an object that has both magnitude and direction, and it's often represented as an arrow in a coordinate system. Examples: force, velocity, displacement. Visual: a simple 2D or 3D vector diagram showing components. Next one, vector operations. While we are adding two vectors, the operation is to head to tail rule. And second one, scalar multiplication. Scalar multiplication is used by changing the magnitude but not the direction. And inner product or dot product, a powerful operation that gives a scalar value for two vectors a and b. The inner product is or dot product is mod a into mod b cos theta. An orthogonal vector. Two vectors are orthogonal if they are perpendicular to each other, and the crucial test, their inner product is 0. Why? Because cos 90 equals to 0. Mod a mod b cos 90 is 0, the product becomes 0. Then why it is important? Orthogonal vectors are independent. We cannot express one as a multiple of the other. They form a basis of a vector space. And what is a signal? A signal is a function that conveys information about a physical phenomenon. Example: sound waves, radio waves, electrical voltages, stock price over time. The analogy: we can think of a signal as a vector with an infinite number of dimensions where each point in time or space is a dimension. Next one, signal space. Just as the vectors live in a vector space, signals exist in a signal space. Next one, this space is a mathematical framework where signals are treated as vectors. Vector operations in signal space. Addition: point by point summation of two signals. And scalar multiplication: multiplying a signal by a constant. And another operation or dot product. For two signals f of t and g of t, the inner product or dot product is defined as integral minus infinity to infinity f of t g star of t dt. The concept of orthogonality: just as two vectors are orthogonal if their dot product is 0, two signals f of t and g of t are orthogonal if their inner product is 0. And integral minus infinity to infinity f of t g star of t dt equals to 0. Analogy check: this is the direct parallel to the dot product of vectors being 0. And why orthogonality matters in signals? Efficiency: orthogonal signals doesn't interfere with each other. This is a fundamental to multiplexing, where multiple signals are transmitted over the same channel without corrupting one another. Signal representation. Any signal can be represented as a linear combination of set of orthogonal basis functions. There are few operations like Fourier transform and Fourier series. This is the most famous example. We represent a periodic signal as a sum of sines and cosines, which are set of orthogonal basis functions. The role of complex numbers. Many real-world signals examples in wireless communication. The signals are better described using complex numbers. A complex signal has a real part and an imaginary part. Analogy: a complex vector in a high dimension space. Complex orthogonal system space. This is an extension of real orthogonal signal space to include complex valued signals. And the dot product or inner product is the inner product definition becomes crucial. Integral minus infinity to infinity f of t g star of t dt. The complex conjugate g star of t ensures that the inner product of a signal with itself is its energy, a real valued number. And thank you for giving me this opportunity.